Thank you. Yeah, so for my second lecture, really the theme today will be around the non-archimedean Milnor fiber. So the idea will be to present a kind of avatar of the Milnor fiber, but in the non-Archimedean world. So it will, for me, I will see it as a semi-algebraic set, but it can also be studied with the structure of a rigid analytic variety. And I will try to show out of this object, we can recover now some known things like the Motivic zeta function, the Motivic Milnor fiber, so things that are like, I could say nowadays, somehow classical invariants that can associate to a regular map. And I will show how the Hrushovski and Kazhdan Motivic integration can help us to maybe say something, maybe not new, but give somehow a new approach to those objects, which are somehow now classical and come from Denef and Loeser. So the idea, so for today, my parameter space will be the field Lorentz series C double bracket T, and it's somehow important to really work over this field. Otherwise, you lose some things. And if we start, so we are interested really in the classical thing. We take f a polynomial in R variables, and so if we are to do a topology as in Patrick's lecture, where we could study the Milnor fibration associated to f, and so say we want to study the hypersurface defined by f equals 0, and suppose that we have some point x here, and everything I will say is true for any x, but it's interesting if x is a singular point of this fiber. And so we have the topological Milnor fiber. So as you've seen in Patrick's lectures, the idea is that you take an open ball. I mean, topologically, you take a small complex open ball around x, and then you take the pro-image of eta, which is supposed to be small with respect to epsilon, so eta close to 0, and you take f minus 1 of eta intersected with the open ball, and that gives you the topological Milnor fiber. And we want to do something similar, but in non-Archimedean geometry. So what's the natural thing to do? So we work over a C double bracket T, and we can define the fx, I will put a none, the non-Archimedean Milnor fiber. So the idea would be to point to take. So I've used this as a semi-algebraic set. So we should call y the variable. So we want to take points in the valued field. And so what do I want for my points? I want points that will specialize to x. So that would be like the analogous of the of the ball of radius epsilon. So the idea, you want to take point y that will specialize to x. So the way to phrase this is to say that the valuation of the of y1 so I want my yi to be in the valuation ring, and I want, once they are in the valuation ring, I can ask that the residue of y. So by this I really mean the residue of y1 up to yn be equal to the point x. My x, so x this, and yeah, x is really in the point, complex point of my special fiber. And okay, so that's the analogous of the ball of radius epsilon, and then I want some.
Sorry, what is the last line?
Residue of y is x. So when you have a point in the evaluation ring, you can just take the residue map to the residue field, and you can ask that this residue is x. Okay, and then I want the analogous of the being in a fiber which is near 0. Well, the natural thing to ask is that f of y here in a non-Archimedean geometry so now we have access to this t, and if you work a bit with variable field, you see that really the interpretation of this t is that it's something non-zero, close to 0, and somehow infinitely close to 0. So it behaves a bit like an infinitesimal, and so it's really the most natural thing to define is to ask that f of y is this t. And somehow you see, it doesn't really matter. I choose t here because it's maybe it's the most natural choice, but I could choose something else, and basically I would get the same thing. Just it makes seems much nicer to work this way. And this object is what is called a non-Archimedean Milnor fiber. It appeared in actually a paper by Berkovich, but from our point of view, it's more in a paper by Nikaz and Sebag. And they show that, so this, for me today, I view this as a semi-algebraic set, but you can also undot it with the structure of rigid analytic variety or Berkovich space or Adic space, if you want to be fancy also. And with this point of view, then you can consider its étal cohomology group, and we have the following comparison theorem. So it appears in print in a paper by Nikaz Sebag, but really the theorem is just combining two comparison theorems by Deligny and Berkovich, saying that we have natural fism between the étal cohomology group of this non-Archimedean Milnor fiber. So I'm supposed to bake chance to the algebraic closure for this to make sense. So it's étal cohomology, so you need to take coefficient in QL bar. But you can think that it's C, it doesn't really matter for us. And this with will be, or I should say, naturally isomorphic to the singular cohomology of the topological Milnor fiber at X. And I should take the same coefficient if I want to be coherent. So we have natural isomorphism between the cohomology of this F. This is like the topological topo. The topological Milnor fiber, and this is the non-Archimedean Milnor fiber. So it means that this somehow most natural thing we've done was the right thing to do. And the isomorphism is also compatible with the action. So on those groups, so you've seen we have the monodromy that acts on those groups. And here, because the analytic Milnor fiber is really defined over C double bracket T, because of functorial properties, we get for free an action on the étale cohomology groups of the Galois group of the base field, and the Galois group is mu hat, the limit of all groups mu n, and if you choose a topological generator of this, then the action of mu hat, then the action of mu hat and of the monodromy will be compatible. So it means that not only the dimension of the group are correct, but also we recover the monodromy action. So the upshot is that out of this object, really we recover all the cohomological invariants we can associate to the Milnor fiber, including things we define using the monodromy. And yes.
What's the exponent of the C double bracket T?
It's alg. It's because this is defined over C double bracket T, but when you take the étale cohomology group, you want to Bayes change to the algebra closure, like in when you do cohomology over a finite field, for example. Okay, and what I want to explain is how out of this object, or maybe some slightly related objects. So in fact, we will use something slightly different. So xf of x will be the point y in VFR, such that, so same condition, y the residue of y is x, but instead of asking that f of y is exactly t, I will just ask it to be close to t. And by close to t, I mean, so one way to phrase this is to say that the valuation of f of y minus t is strictly bigger than the valuation of t. And this condition is equivalent to just ask that the RV, so remember the RV map from yesterday, that RV of, f of y is equal to RV of t. So in terms of if you want topologically, it means that we don't take only one fiber, but we take a small preimage, the preimage of a small ball around t. I don't have a very good, explanation for why we care about this. It's just that for what I want to do, it's better if the set I look at is of dimension r, and otherwise here it was of dimension r minus 1. So it's a bit thickened. But again, if you think about in terms of the Milnor fibration, taking a small disk around T, or if you want around eta, won't really change the topology because you have a fibration. So this still, if you want this one, still really still have the same. You can write this one as a degenerate union of things isomorphic to the analytic Milnor fiber. Yes. Sorry? If y is if y is 2t, no, if y is 2t, 2t minus t is t, and so no, I don't want fy because 2t is very close to is very far from t. Yeah. Well, so for example, my f of y could be t plus t squared, something like that. RV, yeah, RV of f of y is RV of t. What the? Yeah, so RV, yeah. So RV is the map from the non-zero element in the value group to this RV, which was defined by VF modulo 1 plus the maximal ideal. And so an element RV of X equal RV of Y if and only if valuation of X minus 1, Y is strictly bigger, so X and Y must be close, and how close? They must be closer to their own valuation. So valuation of X, which are then forced to be the same as the valuation of Y. Right? So, yeah. Okay, so now I want to explain how out of this object we can recover the Motivic zeta function and the Motivic Milnor fiber. So for this, I need to take a step back and come back to where I ended last time. So it's really about Hrushovski Kazhdan volumes. So I guess that was my 1, it's going to be 2. So at the end of last lecture, we had this isomorphism between the Grothendieck group of semi-algebraic set over K. We have this integral isomorphism to this Grothendieck group of RV with this grading, and modified with this ideal I, which was very explicit. You remember, it was really just saying that you have two ways to get an open ball. Either it's just one point in RV, or it's just one point viewed in dimension 0 plus the full point in RV of positive valuation. Okay, so and the way it was constructed was we defined the lifting from RV to VF, and then and the theorem is that you can invert the thing. Okay, and now I want to explain how out of this we get something in the Grothendieck group of varieties. And the idea is that constructing this is really the difficult part of the theory. And now it's more okay. It will involve some ingredients, but now it's somehow much easier. And the idea is that what you can do is that this Grothendieck group of RV, you can decompose it in something called the res part, which more or less will be the Grothendieck group of varieties. And so this is the part coming from the residue field, and this is the part coming from the value group over some So the idea of this decomposition is that, so first, what are those things? So res, so if I have some point, some object in my category of RV, X, I guess I was trying to keep X for the valued field. So if I have YF in RV, in my category RVN, so meaning F goes from Y to RV to the N, then I say that YF in res, I say that it's in res N if the valuation of Y, so Y is a subset of RV, so I can take the valuation of Y as a component Y as a set, is a finite set. So for example, if my Y completely lives in the residue field, that I'm in res, but maybe my valuation is fixed but not exactly 0. And this, it's also somehow related to the residue field. and that's my res category.
Sorry, what is
Yes.
cancel?
Yeah, I will say in a moment. And gamma, well, gamma is so gamma star is the Grothendieck group of the valuation of the value group. So our value group, because we just work over algebraic closed valued fields, the value group, when we interpret our semi-algebraic set, value group is always an ordered, a dense ordered abelian group. So if you want this Q or some non-standard version of Q, and so definable sets in the value group. If you want, definable sets really just come from piecewise linear geometry because you just have the addition, the order to define things. And so we can also define a Grothendieck group of such things. And there is a subtlety here that I don't want to discuss. And how you relate this with RV? Well, if you have some maybe delta in this in this thing, then you just take the preimage v RV minus 1 of delta. So again, it's component-wise, and that gives you something in RV, and that gives you a class in Grothendieck group of RV. RV. And the map here in this situation will always be given by inclusion. So, and the idea is that okay, so we have this decomposition and the gamma fin. Well, it's just things that are both things of both forms at the same time. So basically, it corresponds to finite sets in gamma. And if you take a finite set in gamma, that you take its preimage, and then by definition, it's also in res. And so you can view it in both categories, and that's the thing over which I tensor. And you can show that it's the only relation between the two things, and that you can build all things in RV out of these objects. So it means that to understand this Grothendieck group of RV, it's enough to understand those two groups. And the idea is that now you can get rid of this of the value group part. If you want to be fancy, you can call this the tropical part, just by taking some Euler characteristic. So you have this Euler characteristic. Maybe you can call chi from this Grothendieck group of to Z, and it's come from the so this in gamma you have really your here it's something a bit weird, but because we're doing model theory, but it's come from it's a no-minimal structure, so you have an abstract way to define the Euler characteristic. And really, the Euler characteristic is defined naively by saying that if you want the points, I have Euler characteristic 1, open interval, I have Euler characteristic minus 1, and then you can build out of this everything by you have some cell decomposition into boxes, and then you can define the Euler characteristic naively this way. But there is a twist, which is interesting, is that in this tropical world, because compared to usual minimal theory, because there is no multiplication, you can also define the so-called bounded Euler characteristic of delta, which will be the Euler characteristic of delta. I should take some. So the idea is that you take the Euler characteristic of delta, but now you intersect delta with some box. So say you are in gamma to the n. And you take a box, and you take the box large enough. So I write as a limit, but really just it means that if n is large enough, then the Euler characteristic here will stabilize, and that's my so-called bounded Euler characteristic. And you can do this in a way compatible with taking the quotient group, but and this you can do this only because you have the you don't have the multiplication. And somehow, if you want for bounded sets, then it doesn't change anything, because if m is large enough, then you recover just the Euler characteristic of delta. But for unbounded sets, for example, if you take 0 plus infinity, so the Euler characteristic is -1, but the bounded one is 0. That's something, and that's really something new. This bounded Euler characteristic, and that's the one we need. And now how we go from this quotient group to the quotient group of varieties? Well, simply by saying that we map this thing to the quotient group of varieties, so over C, and we'll get some action, but with the action of mu hat, but at this level we don't see it, and we just send the class of delta, which is in dimension n, to this bounded Euler characteristic of delta, and then we multiply by the class of gm to the n. Okay, and then on the res category, I will not explain everything, but the idea is that if you have something in res, you're very close to be in the quotient group of varieties, because if you have something in res, you can assume that your y, so if you have yf in this category, then you can assume, so I said that the condition was that the set of valuations was a finite set, but if it's a finite set, you can just, up to cutting into pieces, you can assume that it's just a singleton. You can assume that the y is actually included in v alpha 1, v alpha n, with v alpha is just v rv minus 1 of alpha. So by this, I just mean that those, the valuation of points in y are fixed. And this v alpha, really, you could think of them as, I mean, they are torsor over the residue field, because up to a choice, if you pick a point in V alpha, then you get a bijection with the residue field. But so you can, so when you have a y like that, you can put it in bijection with some subset in the residue field. So, which will be constructible. So you can build an element in a quotient group of variety. But doing this involves choosing a point, and the choice of the point, if your alpha, say your alpha is k over n, because it's always, because our parameters are c double brackets t, here it's important. The alpha will always be rational numbers. And if it's of this form, then the choice of the point and the ambiguity in defining, in making y in bijection with something in as an algebraic variety over the residue field, the ambiguity really just comes from the choice of nth root of unity. And so you get for free an action of mu n in this situation. And it means that out of such a thing, you build a variety plus an action of mu at the limit of all. with the natural map, mu and groups of nth root of unity. And you can show that doing this, so this gives you a way to go also. And this muat is, this muat really appears as a Galois group of our set of parameters. And that's it. And so that's the map. And you can show that for the finite things, it's coincide. And you can also show that it factors through the explicit relation we had above. And so that gives us a way, if we combine the two things, then we get a map vol from coordinate group of VF to the coordinate group of variety over C with the muat action. And that's, sometimes it's called the Hrushovski Kazhdan volume map, but it's called volume, but it doesn't really, it's more like a kind of Euler characteristic, because it's really depend on I mean, you can't ignore smaller dimensional pieces in this picture. So it's really additive without ignoring things of smaller dimension. If you want a true volume map, you need to work with volume forms. So as I was doing at the end of last talk. So so basically the Hrushovski Kazhdan theory works also with volume forms, and the idea is that you decorate everything with mu. So now the category. So maybe coordinate group of this thing. Now the category is objects x omega, x semi-algebraic, and omega is just a definable function to the value group, and I've used this omega like I think of this as a volume form on X, and the thing important is that then now I say that the class of X is a class of X prime omega prime if there exists U, if the dimension of X is the same as the dimension of X prime, and there exists U inside X, U prime inside X prime, such that the complement is of smaller dimension. So if you want, and H from U to U prime, a definable bijection, which is C1, differentiable. And I ask, so I want this differentiable bijection, and then I ask that the bijection is compatible with the volume forms, in the sense that H of such that if you look at omega of X plus, so because it's differentiable, you can take the valuation of the Jacobian of H, so the valuation of the differential at X, and you ask that this is equal to omega prime of H. So basically, you put inside the frame, you embed in the framework the change of variable formula, and then you have this the same Hrushovski Kazhdan map, but now with the volume form. So yeah, I don't describe it explicitly, but for RV, you have the same thing. You can define the same with volume forms, and then you have an explicit. You can lift things from RV to VF, so it's the same strategy. You lift from RV to VF, then you show it's surjective. It's more or less the same proof. Just you need to take care about the volume form as well. And then you show that the kernel is very explicit. And in this situation, the kernel is even simpler because now we don't have the point. So the kernel mu I will just be, if you take 1 point in RV with embedded in RV1, so, and the volume form on it, you just take the form constant equal to 0. Then when you leave this this thing, you get an open ball around 1 of valuation 0. And so the class is that this is the same thing as just lifting a point in RV of positive valuation. Because when you lift this, because when you lift here, you get 1 plus the maximal ideal. And here you get the maximal ideal minus 0. But because of this, and I said that I can ignore stuff of smaller dimension, I can remove a point, and then in my containing group of VF with volume form, then those stuff with form 0 I identified, right? Okay, so it's long story short, it's the same thing as building the one without volume form, but now this one will look like much more like an integration map because again with the version with mu, you can decompose as residue part, as the res part and the gamma part, and now you can define h. Let's call this h tilde m on the containing group of mu. So yeah, I don't write all the detail, but it's the same thing. You get something in the value group with volume form, which just means it's something in the value group, but with an additional function. And you can define specialization. So how do you get rid of this thing? Well, you choose some integer m, and then you define something. So if, well, sorry, it's gamma. So if you take some class delta with function omega here, then you define hm tilde of this thing as, well, the idea is to do to restrict to integer points, but integer points, but points in 1 over mz. So you intersect, you look at delta, but you intersect your delta with 1 over mz. And for point, what could be my alpha here, then I guess if you're in dimension, yeah, let's say embedded in dimension n, and then you take, and then you sum over L, L minus, let me, n, evaluation, no, sorry, I need more space, I should start there. Yeah. So this specialization we will take the sum over point alpha 1 up to alpha n in delta, which lie in with coefficient in 1 over mz to the n, and then we get L to the minus, I will explain why we do this, valuation of alpha 1 plus summation of alpha n plus omega of alpha. Is it the right thing? It's yeah. Okay, and then you need also the L. N. Okay, so what I'm putting this formula here. Really, the idea is that if you have a point in here, when you lift to the value field, you get an annulus of some radius given by alpha, and you know this radius. And basically, you know the annuli. You can write it as a decomposition of a union of balls of radius given by alpha, and so those balls, a ball of radius alpha should have a closed ball of radius alpha should have volume L to the minus alpha, and because you have annuli, we get this L minus 1 factor here, and this should be interpreted in the continuous group of varieties. So there is no action, but then I will naturally we live in some group here, where we invert L, and we need to also invert 1 minus 1 to the alpha, for alpha an integer, positive integer, and because, so this a priori is an infinite summation, but because delta is piecewise linear, only thing that can appear here is a geometric series. Then you can formally sum these geometric series as things of this form. And L, as always, is the class of the affine line, and really this L minus 1 is the class of the multiplicative group. So I'm doing something very similar to maybe a p-adic integration or a classical Motivic or Denef-Loeser integration, but here I'm only summing at the level of the value group, so it's very somehow easy to define. And for the rest part, then it's easy. I just take. I also look at the valuation of my thing, a bit like here. I look at the valuation of my points, and if the valuation is divisible by n, I take the class, normalized by L to the minus dimension. If not, I define 0. And so this way, you define a map composing everything. You define a map HM from governing group of VF with volume form to this governing group of varieties. And this one, a variety over C, I will call it loc because I have this localization. And you can think of this thing. Okay, and I should say that this process, okay, maybe this process I can do it, but maybe also it will diverge if for example, if my volume form is constant and or is not well chosen, or my set is too big. So maybe it's not defined everywhere. It's defined on so-called integrable things. So I will just make add something here, saying that it's not defined everywhere, just for I should call it integrable. And the idea is that this thing you can interpret this map as really the integral of x. You take the C double bracket T 1 over m points, and you integrate the function L to the minus omega on this set. So for example, if you take m equal 1, you recover something very close to, I mean, you somehow recover the Motivic or Denef-Loeser integration. Plus, you don't have maybe the full package of things, but at the class in the coding group, you get the same thing. And when you look at, but the interesting part of this thing is that you can also look at ramified arcs if you want, so in extensions, and you get also integrals. And this is useful because out of this you can recover. Yeah, so here, let me erase this thing. So
what is the power in the old series is e to the 1 over m in the last line?
This one?
Yeah,
t to the 1 over m. So I look at points in the totally ramified extension of degree m. Yeah, and this m is the m here. Yeah. So then we have the following theorem, is that we can actually recover the Motivic zeta function out of the non-archimedean Milnor fiber using this. So maybe, yeah, okay, I wrote theorem, so now I need to. So first part is that if you look at hm of this x f x. So now I'm back at in my context related to the Milnor fiber. So I have my polynomial f. My polynomial. So just polynomial with convex coefficients in R variables. I had this non-archimedean fiber, but then I said I need to look at this version, a bit second version of this, so this kind of tubular neighborhood, xfx, and then this will be equal in the localized Grothendieck group of variety to the contact loci, so fxm, that I will define in a moment, minus rm, and to the volume of fx is psi of fx. So I need to explain what are those things. So these are the contact loci. And this is a Motivic Milnor fiber. So how are they defined? So this x, f, x, m. So you can, the way you define them is as a subset of some truncated arcs. And so this has arcs in L, M, A, R, such that phi of, yeah, I'm using it the wrong way again, but phi of t, wait, and phi equals t to the m mod t to the m plus 1, and we are.
I think it's f of phi.
Yeah, thanks, François. Where these truncated arcs. So the C point, so it's C points of this are the L, R, So C bracket T modulo T to the m plus 1. So you take a polynomial, but then you look only up to degree. I mean, you identify polynomials if they coincide up to degree m, and the contact loci is the arcs or truncated arcs that specialize. So if you can always specialize t to 0, so you say that the arcs specialize to x, the point we care about. And then you look at f of phi, and just you can replace in phi expression, expand, because f is just a polynomial. You expand, and you ask that all the coefficients below t to the m are 0, and the coefficient of t to the m is 1. And you don't care about higher order coefficients. So those are the contact loci, and it's and the Denef Loeser Motivic or Motivic theta function, at least well, on x. Yes. So usually you don't put this condition here, but yeah, to simplify, I just write only one function. Is this power series of. So you take the class of these things, and you normalize by L to the minus R m t to the m. And so then a priori you view this as a power series in continuing variety, and those are naturally ended with an action of mu n. So if you want, you can keep track of this action. So you use this as a power series here, but from Denef and Loeser work, this is actually rational in a sense. You can make precise, and it's rational, and we understand well the degree. So you can define, well, they define the Motivic Milnor fiber as minus the limit when t goes to infinity of this Motivic zeta function. And this is the Motivic Milnor fiber. And I guess at the time of the paper by Denef and Loeser, it was done only, it was, the proof of the rationality and was done working with a log resolution, so embedded resolution of singularity of f equals 0. And basically, on a resolution, you have an explicit formula for this thing, and then you can formally take the limit, so you get an explicit formula for the Motivic Milnor fiber. And okay, so this is just a definition, it's super weird. If you look at, out of this definition, it's very unclear why this object is called the Motivic Milnor fiber. And I think, but they justify the name by showing that, for example, the Euler characteristic of this is equal to the Euler characteristic of the topological Milnor fiber. And the way they prove this is they look at a compo formula for the Milnor fiber, so that's that comes from Patrick's lecture, the explicit decomposition of a compo of the Milnor fiber. And they look at their formula using a log resolution, and they show that they get the same thing. And I think that this theorem somehow explain, especially maybe the second part, explain that, well, indeed, this object can be naturally recovered from a non-archimedean object, this non-archimedean Milnor fiber, that indeed very much looks like the Milnor fiber, and that it has all the, it remembers all the cohomological invariants associated to the Milnor fiber. So for me, so you can, maybe nowadays we could define things backwards and define the Motivic Milnor fiber out of this non-archimedean Milnor fiber, and then relate back to the invariant computed by Denef and Loeser. And just maybe to few words. So the proof is so the proof of one is very easy because out of the definition of HM, you can just see that this thing will give you this. You don't have anything to compute, and that's the reason for why we take the second version because it's a bit thick, and so when you mod out by L to the by 2t to the m, or because it's ramified, you need to mod out by t to the m plus 1 over m, but then the contact loci appears naturally. 2 is more involved, and it's a bit unclear, and it relies on so it's really so the proof I'm explaining here is from me on Yimuyin. Well, you can also prove this explicitly using a resolution of singularities again, but since I'm trying to not using exact formula, and this was done by Nikes and Payne myself. But you can prove this also without explicit formula by device somehow interpolating between the two Hrushovski and Kazhdan integrals, the one with volume forms and the one without volume forms. And we show that for some special kind of objects, and the non-archimedean Milnor fiber is one kind of such special objects, we can interpolate the two integrals, the one with volume forms and the one without volume forms, and in such a way that that for all those objects you have this, you can do this, you can compare the volume and the limit of the delta function you can associate to this object, and so that they coincide all the time. And next time I will try to explain a bit. So yeah, when we're working on this, it was mostly to justify this. But next time I will try to explain a bit something a bit different, but that also involves this limit process. So it's about the problem of studying integral on singular variety defined as quotient of smooth varieties by linear groups. Thanks.
Time for a few short questions.
Since you are trying to avoid using resolution of singularities, does the theorem work in positive characteristic?
No. Yeah, so that's we would like, but unfortunately the Hrushovski and Kazhdan theory does not work in positive characteristic. Okay. It's really only for equicharacteristic 0, which is a bit sad. Even in Hrushovski and Kazhdan, strictly speaking, doesn't work. But well, in mixed characteristic, you have the work by Kluckers and Loeser on for Motivic integration. But the thing a bit surprising is that the model theory part, so the ingredients, Robinson quantifier elimination, works in positive characteristic. So first, I think there were hopes that you could try to make work the Hrushovski and Kazhdan integration in positive characteristic, but so far nobody has succeeded into making it work because you have problems. I mean, I tried without luck. I mean, it doesn't mean that it's not possible, but I think, hopefully something can be done. But.
Okay, thank you.
Also, you have more complicated ramified extensions.
That's the thing. The problem is that even you understand well the theory of algebraically closed valued field, the way the Hrushovski and Kazhdan theory works, you need to take into account, really all extensions, and so somehow it sees the geometry also of fp double bracket t, and this from the modern theoretic point of view we don't understand at all, and so that's the problem.
Other questions or comments?
Yeah, to say a bit more about what Arthur just said.
You have to speak in microphone. If you want to be heard. Depends on you.
Yeah, I mean, in the quick-arithmetic P situation for definite number sets in VF, there is even no clear notion of dimension. So, I mean, you can have definably isomorphic sets which don't have the same dimension, so to speak. So from the very start, you are in a bad situation to try to mimic the Hrushovski and Kazhdan theory.
Questions again? Okay. So we thanked again the lecturer. And